Good morning. So today we will start with a new topic in heat treatment chapter, and the topic is surface hardening or hardening processes. That is, what we are concerned about is how to improve hardness, wear resistance, and also retain the hard surfaces have better corrosion resistance. Therefore, hardness is improved, that is, surface hardness is improved, so that we can have a better surface corrosion resistance. Now, what are the components that require heat treatment on the surface hardening heat treatment? We are talking of which type of heat treatment? Surface hardening heat treatment. So, gears require surface hardening heat treatment. Bearings require surface hardening heat treatment. Valves require, in some selective areas, surface hardening heat treatment. Cams, hand tools, rolls. So these are some of the mechanical equipments or components that are being surface hardened. So surface hardening techniques are classified into two major categories based on whether the chemical composition of the material at the surface remains same as the parent material or it is changed so that we have a different chemical composition on the surface and a slightly varying chemical composition for rest of the part of the material or component. So gears, where do we need surface hardening in gears? We need to give surface hardening on this gear surface, not throughout, on the interfacing surface. That is, these are the wearing or interfacing surface to allow better wear resistance. We have to give a surface hardening treatment to the gear objects or gear components. So what are different methods for surface hardening? So one of the method is called as case hardening method. And in case hardening we have different methods based on the raw material that is used for generating the hardness on the surface. So first is carburizing, where carbon rich material is coated on the surface of material to be hardened, and it is operated in a required temperature cycle and time cycle so that at the end of the process we get a hardened surface up to 10 to 20 microns or up to 100 microns. This depends upon the time cycle and the temperature cycle that we have used. Nitriding is another surface hardening, or typically we call it case hardening process, where nitrogen gas is used to give better surface hardness on the material. Then we have carbonitriding. Carbon and nitrogen both are used for imparting surface hardness. We have cyaniding, where cyanide gas or cyanide is used. It is a harmful poisonous gas and therefore high level of care is to be taken while operating this particular hardening method. So what is carburizing? Carburizing is a hardening process in which carbon is introduced into the surface layer of the steel. What it is? We are adding carbon on the surface. The steel is heated in contact with the surface that has high carbon content. So what is the add-on over here? That your surface is coated with some material that contains high carbon. The steel is heated to a temperature above upper critical temperature, and that is in the range of 850 to 950 degrees centigrade for a suitable period of time. Now, how do you detect or how do you decide this suitable period of time? We decide it from the depth of the part or the thickness that is to be hardened from the surface. When thereafter, as we have in our cycle, the complete component is quenched to produce hardened surface or a case, and this hardened surface is called as case, and therefore this particular process is also called as case hardening. The steel is then tempered to have the desired hardness throughout the material. Then, so quickly revising, what are the stages in carburizing process? Steel is heated to upper critical temperature. It is coated with the earlier, sorry, we'll start with first step. The steel to be heat treated is coated with a carbon rich powder. This coated material as a whole is heated to a temperature up to 950, that is upper critical temperature. It is held for a suitable time. Thereafter it is quenched and finally it is tempered to give the required hardness. Okay, so this is about carburizing process. Now we will look at second process or slightly more details of the carburizing process, wherein carburizing is again of three types. You have gas carburizing, packed carburizing, and liquid carburizing. So carburizing is done on low carbon steel where the carbon is less than 0.25%. The carburizing time varies from 4 hours to 70 hours. It means it is a long duration process. It takes lot of time. The length of time the steel is left in the furnace determines the depth of the carburizing. That is how what is your holding time at the upper critical temperature defines or controls the depth of the hardness. Case depth ranges from 0.08 mm, that is 80 micron, to 6000 micron, that is 6.4 mm. This is specified based on the surface requirement of the service condition of the products. The carburizing process does not harden the steel, it increases the carbon content to a desired depth up to the surface and thus it improves the hardness. Now second is packed carburizing. That is, we have seen carburizing. There are three processes in carburizing again based on what is used for carburizing. what is used to improve the carbon content on the surface. So in packed carburizing, the steel piece is packed in a steel container and completely surrounded with charcoal. So charcoal is a very high carbon containing material. Charcoal is treated with barium carbonate, which promotes the formation of CO2. CO2 reacts with low carbon steel surface to form atomic carbon, which diffuses into the steel. You can write down these processes in the bullet points so that it will be your reading material and you will be able to remember the things. Thereafter, quenching is difficult in carburizing. Usually, in pack carburizing, usually the part is allowed to cool slowly and then hardened and tempered. So, because these things are in a pack condition, it is difficult to remove the hot component and quench it. Therefore, we generally allow it to cool in furnace and thereafter tempering is done. So what is the time? Carburizing time is around 4 to 10 hours. Carburizing depth that can be achieved does not have any limit, but it is always greater than 1.3. That means if you want a carburizing depth of 0.5 mm, you cannot use this process. Next is gas carburizing. Carburizing is done with carbonaceous gas such as methane. Carbonaceous means carbon containing gas such as methane, ethane, natural gas or propane at about 930 degree centigrade, which is upper critical temperature and slightly above the upper critical temperature. The advantage of gas carburizing is that the steel can be quenched directly from the carburizing temperature. Liquid carburizing. Here, the solution used is liquid, that is sodium cyanide. Shorter carburizing time compared to pack and gas carburizing. Environmental hazards of salts that are used, that is cyanide. Then we have next process that is called as nitriding, wherein ammonia gas is used to give nitrogen content in the on the surface, and this nitrogen content helps in developing surface hardness. So we'll just quickly go through this process. A nitriding steel part or piece is heated in furnace up to 500 to 600 degrees centigrade, and at the same time it is exposed to ammonia gas. The heat from the furnace causes the ammonia to decompose into hydrogen and nitrogen. Nitrogen reacts with the elements in the steel to form nitrides. So what is important over here? The nitrogen from ammonia reacts with the steel to form the nitrides on the outer layer of the steel, providing high hardness and wear resistance. The time range is 1 hour to 100 hours depending upon the steel composition and depth of hardening desired. It is also a long duration process, but it is clean process. Since nitriding does not involve austenitizing the steel and subsequent quenching to form martensite, it can be carried out at comparatively low temperatures and thus produce less distortion and deformation. You see, this is the diagram, schematic diagram. There is a furnace, heating element, and the area where you have to hold the part components. And in this area, this is confined or airtight area wherein ammonia gas is constantly given into, that is, the chamber is filled with the ammonia gas, and it has only one outlet to go out, and that outlet is also coming out through. So this is a diagram that shows the different parts or different setup for process of nitriding. Next element or next is a small modification in nitriding where we call it as carbonitriding, and here we are giving, okay, so this process we have an additional element, that is carbon, along with ammonia, that is nitrogen plus carbon, both are added to the surface at the upper critical temperature, that is 700 to 800 degrees centigrade, and quenching in gas which is not as severe as water is carried out. The result is less distortion of the material to be treated. So now it is a continuous process. You see, you have carburizing gas, ammonia, you have preheat temperature, neutral gas, carburizing gas, and then the last chamber again is neutral gas. Here the temperature is different. Here the temperature is 700 degrees centigrade. Here it is preheat around 200 to 300 degrees centigrade. And when the component moves, it falls into the pool of liquid which quenches it. So you can directly get the material. So this process is generally uses partial automation and for small components which are requiring a continuous hardening process. Okay, so next topic is cyaniding, and this process we have seen again. So cyanide is given in the form of cyanide carbonate and chloride salts, and then the part is quenched in brine, water, or oil. So this thereafter we are here with one more hardening, surface hardening technique, which is called as selective surface hardening. These processes are also called as localized heat treatment because only the surface is austenized and quenched to produce martensite. The basic requirement for this process is that the steel must have sufficient amount of carbon and hardenability to achieve the required hardness at the surface. So medium carbon and high carbon materials are suitable for such processes. Selective surface hardening are also classified according to heat source, that is heating that is used, or method that is used for heating the local surface. One of them is flame, and it is called as flame hardening. Oxyacetylene gas or oxymethane gas flame is used for heating the localized surface, and this surface is then quenched immediately after pouring water or brine or using cold gas. Okay, so this is the basic methodology. Induction hardening. Induction is the method for heating the localized surface, and thus rest of the things, that is quenching, remain same. Laser hardening, where laser is used for hardening the surface. Laser hardening gives you an accuracy of about 1 micron, 1 mm And so, that is, if you want a small surface of around 1 or 2 mm throughout the circular part, or you want to make a strip of around 5 mm by 15 mm, that requires a different hardness compared to rest of the part, laser hardening can be used. Electron beam heat treating, again, instead of laser beam, electron beams are used for heating, and balance process remains same. Here, sometimes in this process, liquid nitrogen is also used as a quenching media. So selective hardening is applied because of one or more of the following reasons. Parts to be heat treated are so large as to make conventional furnace heating possible. That means the parts are very large and cannot be placed in the furnace. Quenching is impractical and uneconomical. Example are large gears, large rolls, and dies. These are the components wherein only small part of the component is required to be hardened and rest of the thing remains as it is. Only a small section or area of the part needs to be heated or heat treated. Typical examples are end of the valve stems and push rods and the wearing surface of the cam and lever. Okay, now I hope you know or you are aware about the names at least of these components, that is valve, valve stem, push rods, wear surface of cam, that is cam and levers. Better dimensional accuracy of heat treated part is achieved. Overall cost saving by use of inexpensive steels, that is low cost steels, to have the wear properties of alloyed steels. That means medium and high carbon steels, which are low cost steels, can be given a very good hardness property which gives them or which makes them wear resistance as good as alloy steel material. So this is the diagram. We'll have this is the flame hardening. You see the setup itself is such that the flame is going ahead and quenching water is being sprayed through the same setup. Okay. Another setup wherein this is the part component which is to be hardened. So from one surface, one side, you have a heating element. This is your work. So there is a flame going on, and on the other side, you have water that is being quenched. So you have support, and the heating flame is moving up. Part is stationary. Okay. So there can be for flat surface, for rounded surface, depending on the requirement of the design and availability of space. You can have different setups for flame hardening. Second is induction heating. Induction, that means an electric power is given. The magnetic field due to this electric power generates heating and it creates a very high temperature in localized area, and this localized area heated component part is quickly dropped into the quenching bath. So this is the process and setup that is followed for induction hardening process. Now we'll just have a look over what are the heat treatment and case hardening and what are the parameters that change. So carbon content zero point 0.4 to zero point 0.6 heat treatment is possible. Case hardening only for low carbon steel, or they are austenized on the surface, they are austenized overall, that is throughout the material. Speed of procedure, that is what is the time taken. This is done in few seconds. This requires 10 hours and more or less. That is a slow process. Surface chemistry does not change. In case hardening, surface chemistry changes as the carbon content is increased up to 0.8 to 1% of carbon or nitrogen is added. Depth is 1 to 10 mm, here it is 0.5 to 2 mm. Surface hardness, that is the hardening scale RC, Rockwell 57 to 60, here you have 65. Microstructure of the surface or material becomes martensite, maybe through the part, that is throughout the part. Here the microstructure is also martensite with central part being pearlite. Control is difficult, here it is easy. Then residual stresses, surface is compressive. Surface is having compressive residual stress. Here also you have surface and compressive residual stress. Core is having medium to high carbon. Here it is low carbon. And cost, it is comparatively cheap. Here cost point is not taken into consideration because the setup costs are very high. Now we'll go to the process advantage, disadvantage, and applications of different selective surface hardening processes. So what is the process? For induction hardening, induced current is used. Metal will be surrounded in a quickly charging coil, quickly changing magnetic field coil. Their heating temperature is around 750 to 850 degrees centigrade and quenching media is water. What are the advantages? No scaling effect, reduces distortion, consistent surface texture, and the disadvantage is it has high cost involved because the induction heating setup is a costly setup. Application: crankshafts, gears, automotive components which require high core strength. We have next process, that is flame hardening. It is heated to gamma region, that is austenite region. That means temperature is around 700 to 900 degrees centigrade, although it is not controllable by using oxyacetylene flame and then immediate quenching. A thin surface hardening takes place. Thickness control is difficult but can be achieved. What are the advantages? There are no scaling, it is cheap and portable. Disadvantages: overheating can damage the components. Applications: again, crankshaft, gears, automotive components which require high core strength. Now you can have a quick look at various process and a comparison between the process variables, characteristics, and applications of various surface heat treatment processes. Starting with carburizing process, the temperature is 900 to 1000 degree. What diffuses? Carbon is added on the surface. Process media, pack, salt, gas or fluidized bed. As we saw, there are three methods of carburizing: pack carburizing, gas carburizing and liquid carburizing. So when it is a pack carburizing, we are using a mixture of salt. When it is gas carburizing, we are using ammonia gas. When it is fluidized liquid, we are using a liquid containing carbon and ammonia. Which type of steels can be treated? Low carbon steel, mild carbon steel, and low alloy steel. Case characteristics: medium to deep gases. Oil quenching is done. Typical surface hardness is 650 to 850 HV. Vickers test after tempering. So there is a disadvantage that tempering is required after completing the process. What are process characteristics? Care is required to minimize distortion, and you have application. So similarly, you have different characteristics and process parameters that are summarized for carbonitriding. I'll just look into temperature, other things can be read out. Okay, so temperature for carburizing is 900 to 1000 degree, carbonitriding 800 to 900 degree, nitriding 500 to 550 degrees centigrade, and nitrocarburizing, this is used for ferritic steels only, and the temperature is 500 to 560 to 570. Now this means that these are the two processes, nitriding and carbonitriding. They don't have austenizing phase transformation. For carburizing and carbonitriding, the temperature range is where austenizing takes place. So in these two processes, austenizing is the main methodology of imparting hardness. So again, just have a comparative look between the surface hardening processes: induction hardening, flame hardening, carburizing and nitriding. Does not change the chemical composition for medium carbon steel and alloy steel. Flame hardening also does not change the carbon content or surface composition. Carburizing changes chemical composition, addition of carbon on the surface. This is the oldest, cheapest technique for low carbon steels. Nitriding, it also changes chemical composition by addition of nitrogen to form nitrides on the surface using ammonia gas. So what are the classification? As we had done, two types of surface hardening processes classified based on whether the chemical composition of surface changes or chemical composition of surface remains same. Okay, so how do you select a right surface hardening method? Carburizing is best method for low carbon steels. Nitriding is a lower distortion process than carburizing, but it can be used for certain type of steels such as chromium moly alloy steels only. Flame hardening is preferred for heavy cases or selective hardening of large machine components. Induction hardening works best on small parts, small enough and suitable in space to be compatible with the induction coil. That means the component should not be too large. We have a coil that can accommodate a component, then only that type of components can be hardened using induction hardening process. Low electron beam and laser hardening are having limited to the low alloy steels and plain carbon steels. Although these are costly methods and the technology involved is also very high. Okay, so we have almost finished today's work for hardening processes. So all the hardening process have been discussed today. Yeah, so if you have any questions you can ask. Queries can be addressed. Thank you.